Hello students, welcome back to the channel. So in this video we are going to be proceeding with part 3 of our organic chemistry series. So in this video we are specifically going to be looking at alkyl halides together with alcohols. So this is going to be a continuation of the previous videos that we have been having about organic synthesis. So make sure that you like the video, share the video to your colleagues, and ensure you discuss all the items that are being presented in this video so that you can get the content to stick in your memory. Now, like we have been doing for other videos, we are going to first start with the preparations. We also look at the reactions, and then later we are going to look at the revision questions. So it's going to be a 3-in-1 presentation. So if you look at alkyl halides, we can prepare them accordingly from different compounds. Now, majority of the things that we are going to be talking about, I've already explained them in the previous videos. So if a reaction is repeating, I'll be just highlighting what we said in the previous tutorials. So if you look at reaction 1, we can prepare alkyl halides from alkanes, but here we said that it's going to take 2 reactions. One where we are going to use ultraviolet light, and we say that for this one in organic synthesis, you make sure that it's going to be your last step. But if at all it's not your last step, we say that we shall opt for sulfur dioxide dichloride, and the condition for that is dibenzoyl peroxide at a temperature of 80 degrees Celsius. So make sure that you add that temperature. So when you're using ultraviolet, we always get a mixture of products, but mainly the main product is going to be a secondary alkyl halide. But when we use sulfur dioxide dichloride under conditions of dibenzoyl peroxide and 80 degrees Celsius, we only get a secondary product as the main product. So for the second reaction, we do not get a mixture of products, but for the first reaction, we get a mixture of products. Therefore, we highly encourage, if at all you are continuing with your synthesis, you opt for the second reaction. But if at all is your final step on the synthesis reaction, then you opt for the first reaction. Now you can also prepare alkyl halides from alkenes, and we looked at this reaction under reactions of alkenes. So we can easily react alkenes with halogen acids or haloalkanes to get alkyl halides. And we say that always these ones are going to follow what you call Markovitch rule, whereby the hydrogen atom adds to the carbon atom with more hydrogen atoms, and then the halogen attaches to the other carbon with few or less hydrogen atoms, and then you form the corresponding product. So we say that the R is going to represent the alkyl group, such as methyl, ethyl, or propyl, and then X is always going to represent an halogen, such as bromo, chloro, or iodo. So reaction 2, this is when you follow Markovitch rule. But when we are not going to follow Markovitch rule, what you call anti-Markovitch, if you are not following anti-Markovitch rule, then we call it anti-Markovitch rule. But for that reaction to proceed, and to do that, we need what we call a peroxide. So the peroxide, we said you may either specify the R or you may just leave it as R. So let's also look at that. So like we explained under reactions of alkenes, this peroxide must be down the arrow because it's a condition. It's not part of the reactants. And for conditions, we say that they must be down the arrow, and then reagents, they must be above the arrow. So when you're adding a peroxide onto that reaction, we follow what you call the anti-Markovitch rule. So here, instead of the hydrogen atom adding to the carbon atom with more number of hydrogen atoms, it adds to the carbon atom. It instead adds to the carbon atom with fewer number or less number of hydrogen atoms. And then the halogen adds to the carbon atom with more number of hydrogen atoms. So that's what we call anti-Markovitch rule, and then we get our product in this format. We can also prepare alkyl halides from alcohols. So for this, we have 3 We have specifically 3 reactions, but we are going to specialize with the first reaction simply because these other reactions have issues in marking. For example, we no longer encourage or we no longer allow students to use reflux in organic chemistry. And also the conditions of the spelling of pyridine confuses a lot of students. So for these 2 reactions, we are going to first ignore them for a moment. However, I address them simply because they will be marked in UNEB, but the moment you use reflux, you'll be penalized almost a 4 mark. And that's quite dangerous. So we shall be going with phosphorus pentachloride, which does not require condition, but rather it replaces the hydroxyl group with the halogen atom for us to get our alkyl halide. So now after that, let's also look at, so we are looking at only a single alkyl halide. So let's look at how we can prepare the dihaloalkanes. Now remember, for us to get 2 halogen atoms on an organic compound, we need to have an alkyne, or simply we need to have an alkene and then react it with an halogen element in presence of an inert reagent. So let's look at the first reaction, which can be from alkenes. So we react alkenes with halogens in presence of an inert reagent, which is going to be carbon tetrachloride, to get our dihalide. So for instance, if you look at this reaction, X can either be bromine, chlorine, or iodine. So for us to get a dihalide from this alkene, we have to introduce an inert reagent, which is going to be carbon tetrachloride, for both of these 2 atoms in this molecule to react with alkene. And then we end up getting our dihaloalkane. Then you can also get them from alkynes. So alkynes can easily give us dihalides simply by reacting it with an halogen acid. And when you do that, remember that here we follow anti-Markovnikov's rule. So for this, here we are going to follow Markovnikov's rule. Hydrogen adds onto the carbon atom with one number of hydrogen atoms. So they become 2, and then 1 chlorine, 1 halogen atom adds onto the other carbon atom. But remember, when you're looking at alkynes in the notes on this channel, we say that alkynes undergo 2 steps reactions. So another reaction takes place whereby another molecule of the halogen acid, the hydrogen ion or the hydrogen molecule or the atom attaches to this carbon atom again, and then the other halogen atom attaches to this carbon atom again. And then we end up getting a gamey dihaloalkane. Now we can also prepare dihalides from carbonyl compounds. Now for carbonyl compounds, we simply use phosphorus pentachloride. Now always remember, when you're using phosphorus pentachloride, we do not require any condition for this reagent. So what it does is that it takes away this oxygen atom, and then one bond of which was attached to this oxygen atom bonds with 1 chlorine atom, and then the other bond also bonds with another halogen atom. So we end up with a gamey halide in this format. It's gamey because both of the chlorine atoms attach to the same carbon atom. So let's say this is going to be valid for both aldehydes together with ketones. So having looked at the preparations, now let's look at or proceed with the reactions of the alkyl halides. Now we looked at alkyl halides in the previous videos, and we saw that we can use them to prepare alkenes, we can use them to prepare alkynes, and we can use them to prepare alcohols. So here we are going to repeat basically the same thing. So whenever you're having any alkyl halide, the most common reaction is heating with sodium hydroxide, but we say that we no longer allow reflux in organic synthesis. So whenever you see reflux, you replace it with heat. So whenever we are having sodium hydroxide and you want to convert an alkyl halide into an alcohol, first you have to write sodium hydroxide and then you have to give it a state which is going to be aqueous. And then the condition for that is not reflux, it must be heat. And whenever you use sodium hydroxide, always specify its state, because we have sodium hydroxide in solid format and we also have that one in aqueous format, and both of them and either of them is used for different use. So converting an aliphatic alkyl halide to an alcohol, we are simply going to use aqueous sodium hydroxide and then we heat. So the condition must be heating, do not use reflux. So I think we can also prepare them from tertiary alkyl halides. But for tertiary alkyl halides, we don't heat with sodium hydroxide. For this case, instead of sodium hydroxide, we heat or we boil with water. So the condition is going to be, the reagent is going to be water, and then we are going to boil. Now this is very common in both UNEB and in mock bodies, simply because for tertiary alkyl halides, for us to prepare an alcohol, we have to just boil it with water, not sodium hydroxide. And when you do that, you're going to get a tertiary alcohol. We can also look at the reaction of our alkyl halides together with alcoholic potassium hydroxide. Now this is a reaction we looked at in alkenes under their preparation. So remember that for this reaction, we say that for this reaction to be possible, in your compound, in your organic compound, you must be having more than 2 carbon atoms. That's why I place here this R and introduce 2 carbon atoms already, showing you that for this reaction to be possible, you must be having more than 2 carbon atoms. If you're having less than that, we are going to form an ether. We do not form an alkene if you're having less than 2 or less than 3 carbon atoms. So you have to take note of that. I've overemphasized this because it's a very common mistake. And then we say that for this reagent, arrangement of reagents is going to be potassium hydroxide stroked with ethanol. Ethanol is also a reagent, so make sure that you place it above. And then the condition is going to be heat to get the desired product, which is going to be an alkene. But always remember that for this reaction to be possible or for you to use it, you must make sure that in your compounds which you have synthesized, you are having more than 2 carbon atoms. Now the other reaction that you are going to look at is going to be a reaction with alkyl oxides to form ethers. Now this reaction is going to be most common with sodium phenoxide because that's where UNEB puts its emphasis on. So we are going to look at a reaction that is going to give us sodium phenoxide, and then we tell you to prepare maybe ethoxybenzene. So for this case, we just need to introduce our alkyl halides. For example, you can introduce bromomethane. So what happens is that sodium reacts with the halogen to form sodium bromide, and then this methyl group attaches to this remaining phenoxide to form our methoxybenzene. I hope that is clear. So it's what we represented here, that if you're having a compound in that form, such as sodium phenoxide, and introduce your alkyl halide, what happens is sodium reacts with this halogen atom, and then the others attach to themselves to give us the final product. So I made a note and say that secondary and tertiary alkyl halides are going to give mainly alkenes because they easily undergo elimination reactions. Now for this case, we are talking about the reaction that we have just described above, whereby the reagent, which is ethanol, is going to first react with potassium hydroxide to give us a compound of this form, an ion of potassium, and then later they react with our alkyl halide to give an alkene, which is a reaction we are just from looking at. I hope you know the mechanism because we looked at it under alkenes. Now the next reaction is going to be a reaction between potassium cyanide, between alkyl halides and also potassium cyanide. Now also for this reaction, just like the previous reaction, potassium cyanide must be stroked with ethanol. So ethanol is not a condition, it must be above the arrow. So potassium cyanide stroked with ethanol, at a condition of heating is going to, what happens is that the halogen atom gets replaced by the cyanoion, and then you form a nitrogen. So I made a note and say that this reaction is always going to increase the length of the organic compound by 1 carbon atom. So we only use this reaction usually during preparation of carboxylic acids or preparation of alcohols, because when you're having an alcohol you can get a carboxylic acid, and when you're having a carboxylic acid you can get an alcohol, and we shall be looking at that under the revision questions. So we continue and say that secondary alkyl halides are going to form mixed products, but tertiary alkyl halides give only the elimination product because the cyanide ion is going to be a strong base. But mainly we are going to look at this reaction in the examination bodies when you're dealing with primary alkyl halides. So for the secondary alkyl halides and tertiary is going to be a very rare case. So part C is going to involve the reaction between silver alkanoates to form esters. Now we are going to look at this we looked at this elaboratively under the esters video, preparation of esters, and it's a very good reaction to be examined. So you can easily get your alkyl halide and then react it with a carboxylate, a silver carboxylate ion to form an ester. And you saw that we looked at this reaction. It's not very common in synthesis. It's only common in mechanisms. And we looked at it elaboratively under the esters video, still on this platform. Now the other reaction, which is very common, but again very rare to be given by teachers, is going to be the reaction between alkyl halides together with ammonia. So ammonia reacts with alkyl halides in presence of ethanol, and then we heat in a sealed tube. Now for this we get a mixture of products, but the main product is going to be the amino product. These ones are going to be very minor products. So whenever you're preparing an amine, always ensure to use ammonia, but it must be in ethanol, and then you heat in sealed tube. That's the condition. The condition must be that the heat must be subjected in a sealed tube, simply because we are going to get a variety of products, but the main product is going to be an amino product or a secondary amine, and then the others are going to be the secondary, and the tertiary amines are going to be very minor. So this reaction is going to be very important under benzene and its derivatives, where we look at aminobenzene or phenylamine or aniline. So the next reaction we are going to look at Grignard synthesis before we look at the revision questions. So for Grignard synthesis, we have already explained this in details. For Grignard, you always get your magnesium and then react it with an alkyl halide. What this does is that this magnesium atom or metal adds on to this alkyl halide to get a product of this format. But you must make sure that the condition for that is going to be dry ether. Now in the notes of carbonyl compounds, we say that to eliminate this, you simply introduce acidified water. Now there are two ways to write acidified water. One, we said you write water and then you stroke it with the acid. Or you can simply write the hydroxonium ion to show us that this is going to be acidified water. Both of the conditions are going to work. So having looked at that, let's go through these revision questions as quickly as possible. So let's look at or let's write the equations for how 2-bromopropane can be converted to propan-1-ol. So if you look at that, for us to get propan-1-ol from 2-bromopropane, you realize that we need to first form an alkene. But you are forming an alkene from an organic compound that is having more than 2 carbon atoms. That's why we use this reaction. But remember I told you that the alcohol must be above and then the heat must be down. So from here we are going to use antimaconicals because you're seeing here peroxide. When you use antimaconicals, we convert this alkyl halide to an alcohol by heating it with aqueous sodium hydroxide. We say that whenever you use sodium hydroxide, you make sure that its state is mentioned. So proceeding, we can also look at this. So first we are preparing ethanol to propan-nitrile. And to do that, we need a cyanonitrile to get prepared. But before that, you need to first get your alkyl halide. So after preparing an alkene, now this, if at all you're having two carbon atoms, you cannot use alcoholic potassium hydroxide. In the first video, we said you are going to strictly use this one because for this one is not selective in preparation of alkenes. So here we form, now here, either it's anti-Markovnikovs or it's Markovnikovs, it does not matter because you're going to always form the same product. So from here we can form our nitrile. But we say that always this alcohol must be above the arrow because it's part of the reagent. The only condition that you need is going to be heat. So this is going to be the same as the previous one. So make sure that you pause the video and then you take the examples down to stick what you have just discussed above. Now next we are going to look at is going to be what we call halobenzene. Now halobenzene is simply mean and a benzene ring which is attached to an halogen atom. Now to do that we have already looked at this. So let's be very quick when you're describing it in the previous video. So we get halobenzenes simply by getting an halogen and then treating it with an halogen carrier to get an electrophile so that it can attach to the benzene ring. Remember that benzene undergoes mainly electrophilic substitution reactions. That's why we react an halogen with an halogen carrier for us to get an electrophile that can later attach to the benzene ring for us to get an halobenzene. And we said that X for this case is either going to be chlorine, bromine, or sometimes iodine, which is a very rare case. We can also prepare halobenzene from a diazonium salt, and for this one, there are mainly very many reactions. So you simply get the concentrated format of the acid, such as hydrogen bromide or hydrogen chloride, concentrated hydrogen bromide or concentrated hydrogen chloride, and then you react it with an oxide or an halide of copper in the +1 oxidation state. So if it's hydrogen bromide, we are going to stroke it with copper 1 bromide. And if it's hydrogen chloride, we shall stroke it with copper 1 chloride. And then the condition for that is going to be warming. So if you do that, you are going to convert our diazonium salt into an halobenzene based on the reagent you have used. If you have used hydrogen bromide, concentrated hydrobromic acid in copper 1 bromide, you are going to get bromobenzene. And if you have used concentrated hydrochloric acid alongside with copper 1 chloride and you warm, you are going to get chlorobenzene. However, iodobenzene is going to be obtained differently. For this, we are simply going to get potassium iodide in aqueous and then we warm. So remember that the conditions are going to remain the same, but the reagents for iodobenzene, they are going to change. So you simply get potassium iodide in aqueous state and then you warm it with the diazonium salt for us to get the iodobenzene. So having looked at the preparation, let's also look at the reactions that halobenzene can undergo. Now remember, I told you in the previous video of benzene and its derivatives that benzene, when it is connected to an halogen atom, this halogen atom, the bond between carbon and chlorine is very strong, simply because when pairs of electrons on this halogen atom, they interact with the pi electrons in the benzene ring. So the bond between carbon and chlorine, or carbon and the halogen atom attached to it, they are going to be very strong for them to just be merely replaced by any compound or any other atom. So for that, we are going to be using extreme conditions. So chlorobenzene or halobenzene can mainly undergo two reactions. One is going to be the Grignard synthesis, and the other one is going to be aqueous sodium hydroxide under extreme conditions of heat together with pressure. So first we're going to look at Grignard synthesis. So for Grignard, whenever you're having an alkyl halide, you simply get magnesium and then you put it in dry ether. So what it does is that this magnesium attaches to this halogen atom and then we get a phenyl magnesium halide. So for us to remove this the magnesium halide, we simply introduce acidified water, which I told you that you write H2O soaked with an acid, or you simply write hydroxonium ion. So what it does is that it replaces all the magnesium halide with an hydrogen atom. We are going to look at that in the revision questions. Or we can have reaction number 2, whereby we can convert our halobenzene into a phenoxide. And to do that, we need to get aqueous sodium hydroxide at a temperature of 350 degrees Celsius and a pressure of 150 atmospheres. And when we do this, we are going to get sodium phenoxide. Now notice that this one cannot be converted directly to phenol. There's no way you can heat sodium hydroxide with halobenzene and you get phenol. It's not possible because the bond between carbon and chlorine is very strong, according to the explanation that I've given you previously. So we're going to form sodium phenoxide. Now we have a variety of uses of sodium phenoxide. We can either use sodium phenoxide to form phenol, or we can use it to form an ether. So if you want to get an ether, we simply get an alkyl halide. For example, I can use methyl bromomethane. What happens is that this sodium reacts with the bromine atom to form sodium bromide, and then the methyl group attaches to the phenoxide to form methoxybenzene. Or we can form phenol simply by introducing acidified water. Now I've told you that there are two ways of writing acidified water, and for this reaction we need a condition of warming. There are two ways of writing acidified water. You can either write it in this format. Now either you can warm or you may not warm because the room temperature is already 25 degrees Celsius. You can either write it as you can write acidified water as an hydroxonium ion, or you can write it in this form, where you write the water molecule and then you stroke it with an acid ion to give us our phenol. So sodium phenoxide can either give us an ether or it can give us a phenol. Always remember that in your synthesis. So to convert this phenol into benzene ring, we simply heat it with zinc dust. And then we get our benzene. So the other reaction is going to be hydrogenation reaction. Now remember, we said that in the previous video, whenever you hydrogenate in benzene, we are not going to use 150 degrees Celsius, but rather we are going to use 200 degrees Celsius simply because there are multiple pi bonds. So we need quite a higher temperature. So we need hydrogen in nickel catalyst, and then at the condition of 200 degrees, what happens is that the pi bonds or the pi electrons, they get removed and then we get a saturated compound of halocyclohexane. And let's look at the questions to elaborate what you have summarized. So first, let's look at how you can convert 1,1-dibromoethane to bromocyclohexane. So for this, since we're having a cyclohexane, it shows that we need to prepare a benzene ring. So we convert this into an alkyne. Then from here, we convert it into a benzene ring. Remember, we explained all this in the previous video. So we get an halobenzene simply by getting our halogen, and then we stroke it with the halogen carrier. So make sure that the halogen carrier is above the arrow. And for this, we don't need any condition. So nothing should be down the arrow. Then from here, we hydrogenate our benzene ring to get this product, which was required. Now remember, I told you, whenever you're proceeding with the next line, do not use boxed arrows. We do not have boxed arrows in chemistry, but rather use diagonal arrows. Here they were used because it was for elaboration purposes. So for part B, if you look at benzene, preparation of benzene or converting benzene to cyclohexane 1,2-diol. Now remember, for 1,2, let me talk about, we have already talked about all this. So let me talk about this reaction. Let me remind you about this reaction. We looked at this reaction in the first video, and then we say that for you to get diols, you make sure that whenever you're using alkaline manganese 7, you don't heat. Because the moment you heat, you are going to be calling for dicarboxylic acids. And we don't want that. So for you to get a diol, make sure that whenever you use alkaline manganese 7, you do not heat. So these are other examples converting ether into phenol. So this was a little bit real quick, but you need to be very careful with this condition. Whenever you're using sodium hydroxide, you give it its state, aqueous. And then for us to convert an halobenzene to a phenoxide, the conditions must be specified. 350 degrees Celsius or 360 degrees Celsius at a temperature of 150, at a pressure of 150 atmospheres to get our phenoxide. And then you say that phenoxide can either be converted into an ether or phenol according to that reaction. Now here I said dilute hydrochloric acid. Dilute hydrochloric acid, why is it dilute? Because I placed here aqueous. This means that this hydrochloric acid was dissolved in water. So it's the same as a student who has written H2O struck with hydrogen ion, or is the same as a student who has written the hydroxonium ion. So this state here, aqueous, indicates that this is dilute hydrochloric acid, or someone may just say dilute hydrochloric acid to get this product. They are all going to be marked. But if you just say hydrochloric acid without putting the state, you are going to be qualified wrong, because the acid that you must be using must be dilute. So for this example, we also looked at how we can use Grignard synthesis to attain our product. So for Grignard, we have been stopping here. So you have seen here that to introduce our dilute water, you can either use hydroxonium ion or water soaked with the acid ion, or you can simply write dilute hydrochloric acid like this. To give you, what it does is that it removes this magnesium bromide and replaces it with an hydrogen atom, which ends up giving us the benzene ring, and then we form what we want. So we say that when you're using fuming sulfuric acid to get benzene sulfonic acid, always the condition which is required here is not heat but is warming. So always make sure that you indicate that condition. Whenever you use fuming sulfuric acid, always warm to get benzene sulfonic acid. Now lastly, we are going to look at alcohols. So for this also alcohols, we are going to look at their preparations, we'll look at their reactions, and then we also look at their revision question applications. Now for preparation, we can easily prepare alcohols from alkenes simply by using acidified or dilute sulfuric acid. So for this reaction, this is the only reaction where we say that acid is going to come first and then we stroke it with the water molecule. So we make a correction there. So the condition must be down the arrow and it's going to be warming. So for this case, it's going to be acid. Unlike others, it's going to be acid stroked with the water molecule simply because it's the acid to react first and then water reacts last. So we follow Marconi-Covey's rule. This hydrogen ion from the acid goes to the carbon atom with one number of hydrogen atoms. And then the water molecule comes to the second carbon atom. And then we end up with the following product. And we explain this in details under alkenes. So we can also prepare alcohols from alkyl halides. We have already looked at this reaction. But we say that we do not use reflex. Instead, we use heat. So you heat your aqueous sodium hydroxide with an alkyl halide to get an alcohol. So I made the notes here, which I've already made above, that to prepare an alcohol from a tertiary alkyl halide, we are not supposed to use sodium hydroxide, but rather we are going to just boil our tertiary alkyl halide with water. And when you do that, we are going to get a tertiary alcohol. Always remember this reaction because it's very common for both UNEP and MOC bodies. When you are converting a tertiary alkyl halide to a tertiary alcohol, you do not use sodium hydroxide. You use water and then you boil that water with the alkyl halide that you're having, which is tertiary, to get tertiary alcohol. So another reaction is going to be from carbonyl compounds. Now there was a misrearrangement of reagents for this case. So you're going to be terminating all this acidified water. So for condition for this to happen, we simply get our carbonyl compound and then react it with lithium aluminum tetrahydride in dry ether. There is no condition required for this. We are going to get our alcohol. So what happens is that this oxygen atom gets replaced, one bond attaches to the hydrogen atom and the other bond is going to attach to the hydroxyl group, and then we get our alcohol in that format. Similar applies to the ketones. We also follow the same mechanism. It's only lithium aluminum tetrahydride which is required, struck with dry ether. The second reaction may not be necessary. Now we can also prepare our alcohols from carboxylic acids simply by reducing them with lithium aluminum tetrahydride in dry ether. So as we do that, all you need is one reaction, lithium aluminum tetrahydride in dry ether. We also reduce carboxylic acids by removing this oxygen atom, and then we remain with the hydrogen atoms attached to the carbon atoms. So this goes away, and then these two bonds, each of them attaches to the hydrogen atom for us to get our alcohol. So reduce carboxylic acids by using lithium aluminum tetrahydride in dry ether to get corresponding alcohols. We can also prepare them from Grignard synthesis. I hope you have already seen that. By getting the halide of magnesium and then reacting it with the carbonyl group containing the length of the carbon atoms you want to extend your organic compound with. But whenever you're using Grignard synthesis, always don't forget the condition of dry ether. Then after that, to remove this magnesium halide, we introduce dilute acid or acidified water, and while it replaces this magnesium halide with the hydrogen atom for us to get the corresponding alcohol. So you're going to make a note that this is going to always to increase the length of the carbon atom by either 2 or more, depending on which carbonyl compound that you'll be adding to the alkyl halide. So we shall be looking at this in the examples. So if you look at these examples, to look at what we have covered, we are going to convert methanol to propanol. So if you look at this is involving lengthening the chain by 2 carbon atoms, simply because you're starting from meth, which means 1 carbon atom. So to do that, we need to first get a magnesium halide. And to do that, we need to first get an halide, and then we add the magnesium atom. So how are we going to do that? We get our methanol. We say that we are going to be converting alcohols to halides using strictly phosphorus pentachloride. So doing that, we add our magnesium, but whenever adding magnesium, always use dry ether. So after that, we add our carbonyl compound, also present in dry ether. Now after that, we remove the magnesium halide by using acidified water. You can either use dilute hydrochloric acid by writing HCl with a state of aqueous, or you can use hydroxonium ion, or you can use H2O struck with the hydrogen ion to get the final product that was required. So this is going to involve the same case. You follow it up, and then we give you alternative routes, giving you the same thing, showing that you can first try it out on your own, and then you look back at the screen and see whether you have got it right. But make sure that whenever you're using this, you don't forget dry ether. So this is going to be including more examples. So you also look at that example and then you relate it to what you have been covering. Now the next reaction you're going to look at is going to be reaction of both aldehydes and then ketones. Now when you're dealing with carbonyl compounds or when you're dealing with Grignard synthesis, we looked at this in the notes. Under carbonyl compounds, we say that whenever you're dealing with aldehydes, we are going to use an acid, a dilute acid, to remove the magnesium halide. But when you're dealing with ketones, we shall be using ammonium chloride to remove the magnesium halide. So for this, since we are adding an aldehyde, or we are dealing with an aldehyde, we use dilute acid, or H2O stroke with the acid, or dilute hydrochloric acid to give us an alcohol. Also, this one is going to involve lengthening of the carbon chain by 1. It's also part of Grignard synthesis, and we have already looked at this in details under carbonyl compounds. So if you're having trouble with it, make sure that you review that. Now, whenever we're dealing with ketones, in Grignard synthesis, instead of using acidified water or dilute hydrochloric acid, we are going to be using ammonium chloride. So these two are going to involve reactions of Grignard synthesis using aldehydes. And then when it comes to ketones, for ketones, we are going to be using ammonium chloride to remove this magnesium halide in order to get our respective alcohol. So hydrolysis is always going to be by ammonium chloride whenever you are dealing with ketones. And remember that ketones are going to be in the following format. However, also for this case, we are going to be using dry ether. So having looked at that, let's also look at the reactions that alcohols get engaged in. Now, alcohols usually react with sodium metal to give us effervescence of a carrier gas. Now remember, when you're making a video about organic practicals, a summary about organic practicals in theory, we told you that sodium metal detects presence of the hydroxyl group, and what it does is that it represses the hydrogen atom, and then we get effervescence of a carrier gas, which is going to be hydrogen gas, according to that reaction. So both alcohols and carboxylic acids, which have this hydroxyl group, react with the sodium metal to give us effervescence of a carrier gas hydrogen. And then sodium replaces the place of the hydrogen atom to give us a sodium ethoxide. Now the other reaction is going to be with alkyl halides. So alkyl halides, we have already talked about this reaction because we started with that. And we said that we are going to be ignoring these reactions for a moment, and we are going to be strictly using the first reaction. So converting an alcohol into an alkyl halide, we said that we are going to be using phosphorus pentachloride to get the following alkyl halide. Now we also have reactions of alcohols together with oxidizing agents. And the main oxidizing agents that we have is acidified potassium manganate 7 together with acidified potassium dichromate 6. So alcohols tend to get reduced by both acidified dichromate 6 together with acidified manganate 7 to give us the corresponding carboxylic acids. So these ones, after getting oxidized, they give us corresponding carboxylic acids. These ones are very common, and there are very few mistakes done by students for these two reactions. So I won't say much on them. Now for secondary alcohols, whenever they undergo oxidation, they give us what you call carbonyl compounds. Now this is a very common reaction in organic practicals. Whenever you're having a secondary alcohol, and then we tell you to first apply acidified manganate dichromate 6, and then you heat or you warm, and then later we tell you to test or to put a reagent that tests for presence of a carbonyl compound and you get a positive test. Usually it's this reaction that has taken place. So what happens is that whenever any secondary alcohol, whenever it undergoes oxidation by either dichromate 6 or manganate 7 in acidified medium and we heat, we are always going to get a ketone. We do not get aldehydes, we always get ketones. So 3, we are going to also look at tertiary alcohols. not being oxidized. For tertiary alcohols, they don't undergo oxidation. We can also put this in evidence under practicals, because mainly this is going to be practical work. So as you prepare for your paper 2, you make sure that you also read your practical books, because we usually ask this in both practicals together with theory. Now, another reaction of alcohols that is very common, and it's a full paper 2 question, is going to be reaction of alcohols with concentrated sulfuric acid under different temperature mediums. So at 0 degrees Celsius, we are always going to get hydrogen sulfates, and we looked at the mechanism of this under alkenes or under alcohols in the notes videos of organic chemistry in the playlist. We also looked at primary alcohols reacting at 140 degrees Celsius, and for this we say that you are going to be forming ethers. So what happens is that the R group doubles itself by removing the hydrogen atom, and then we form a product of this format. Like I said, we already shown this one in details in the alcohols video in this organic playlist. So make sure that you look that out, because it's a very common question to be asked. Now the other reaction is going to be the reaction that involves formation of alkenes, which is very common for majority of you. And this is where we are going to use, and this is where we use 180 degrees Celsius with the R reagent being concentrated sulfuric acid to reduce alcohols to their respective alkenes. So the number of carbons remains the same, but the hydroxyl group gets eliminated. And for this one, temperature must be specified. That's why whenever you're using concentrated sulfuric acid, we cannot mark if you just say heat, because concentrated sulfuric acid gives multiple products at different temperature mediums. So make sure that you always specify the temperature whenever you're using concentrated sulfuric acid. Now for this is going to be the revision or the revision assessments to elaborate what you have already covered. So you pause the video and then you try to take down the examples. And I think we have already explained each of them. So here you make sure that you avoid this wide reflex. We don't need this. And for this reaction, you don't need any condition. You simply go and you get your ether. So you pause the video and then you try to take down the examples. If you're having any concerns, you make sure that you leave them in the comment section. And for the video to your colleagues or to your classmates, so that you can all benefit as a group. Like the video for it to be forwarded to your fellow classmates. So this is going to be the final example, the final setup, and then we shall be proceeding with another session about organic chemistry to look at other parts that we have not covered in this video. So make sure that you follow up each and every videos to make sure that you're not lost, because I'm looking through everything and I'm not seeing anything to elaborate about, simply because we have already explained majority of the things that I'm looking at here. So it's going to be about your practice, and at the end we shall be providing revision questions for you to attempt, and then you assess your understanding about the tutorials that you have been following. So that was it for this video. Ensure that you like the video, forward it to your classmates, and you leave your areas of concern in the comment section. So we are going to meet in the next tutorial or in the next session. Share the video clip to your classmates and make sure that in case you haven't understood anything or you have a point of concern, you leave it in the comment section strictly. So see you in the next session.